On June 12th, a Boeing 787 Dreamliner from the airline Air India took off from Ahmedabad, India, bound for London, United Kingdom. It was supposed to be just another routine flight. However, soon after takeoff, the plane couldn't stay airborne and crashed in the Megani Nagar neighborhood, hitting 5 buildings and killing 241 people out of the 241 people on board the plane, including the 12 crew members and 19 more people on the ground. Only one person on board the plane survived the terrible accident. According to the preliminary accident report, 2 switches that controlled the fuel supply to the plane's 2 engines briefly moved from the run position or operating to the CAR off position or off. This caused both of the plane's engines to shut down for a brief moment right at the most critical point of the flight, takeoff. The Boeing 787 Dreamliner is among the most modern, safe and efficient aircraft Boeing has built. It's the result of years of research, advanced design and cutting-edge engineering and technology. The Boeing 787 Dreamliner is a wide-body, twin-engine turbofan aircraft with the capacity to carry from 242 to 420 passengers depending on the configuration. With its entire concept being developed around safety and fuel efficiency. And in fact, when it was launched back in 2011, it was the aircraft that consumed the least fuel for its operational parameters compared to all other aircraft, using up to 20% less fuel compared to the Boeing 767. However, the real difference of this airplane lies in the materials used for its construction, being the first aircraft in the world to be built almost entirely from composite materials. The so-called carbon fiber reinforced plastic, or plastic reinforced with carbon fiber, it's a lightweight, strong and rigid composite material made by combining carbon fibers with a plastic matrix, usually in resin epoxy. This combination results in a material that is stronger and lighter than its equivalent weight in steel or aluminum, making it ideal for a wide range of applications and allowing the total weight of the aircraft to be much lower. This directly lowers fuel consumption and improves airplane efficiency. The aircraft includes systems already standard in commercial planes like the full fly-by-wire system, in which, essentially, the commands made by the pilots on the aircraft's control stick are first sent and analyzed by a computer. Only then does the computer send a command for the flight control surfaces like rudders and elevators to move and make the plane turn, climb or descend. This allows flying the plane to be much safer, since the commands made by the pilots must be within certain limits that do not put the flight of the plane itself at risk. Another unique feature of this plane is that many of its systems are electric and not pneumatic or hydraulic, like in all other planes up until then. For example, the air bleed system or bleed air setup. All other planes use bled air taken from the engine to pressurize the cabin, heat the wings, the well-known anti-ice and power hydraulic and pneumatic systems. However, the Boeing 787 lacks bleed air. All pressurization, air conditioning and anti-ice are done by dedicated electrical systems. The operation of the flaps, the brakes, among others, is also electric. As a next-generation aircraft, safety was a top priority, and the aircraft has double and often triple redundancy in all critical or essential systems for its proper functioning. For example, the central flap-by-wire system has triple redundancy, 3 independent computers, each with about 9 processors, all calculate the same parameters. If any of them presents parameters outside the normal flight envelope, it is discarded by the others. The aircraft is also capable of and certified to fly with only one engine for long periods of time. As a general rule, airplanes like the Boeing 787 Dreamliner, the 777, the Airbus A330neo, the A350 and the A380 are considered state-of-the-art airplanes and virtually impossible to crash due to their design philosophy and the heavy layers of safety and redundancy built into their construction projects. The 787 involved in this accident was equipped with two enhanced airborne flight recorders, which are the airplane's black boxes installed in two locations, one in the tail section and another in the front section. Both are similar in construction and record a combined stream of digital flight data and cockpit voice information, both stored on the same device. At 7:43 UTC, the aircraft requests clearance for pushback and engine start. At 7:49 UTC, the control tower asks if the aircraft will use the full length of the runway. Soon after, the pilots confirm using the full length of runway 28. At 8:03 UTC, the aircraft is told to line up with runway 28 for takeoff. At 8:07 UTC, the aircraft is cleared for takeoff from runway 28. At 8:07 and 37 UTC, the aircraft begins its takeoff roll. At 8:08 and 37 UTC, the aircraft reaches decision speed V1 at 153 knots. At 8:08:42 UTC, the aircraft hits its black box's top speed, 180 knots. At 8:09 UTC, the pilots declare Mayday. According to the analysis of the available videos about the moments leading up to the accident, some theories have been raised about the possible causes of the accident. The first of these is that the flaps were not in the takeoff position or that they had been retracted prematurely. However, the preliminary report shows the flaps stayed in the takeoff position 5 until impact. The theory of bird strike, the theory of fuel contamination with something, the theory of total electrical power loss in the plane, and the theory that the throttles were brought to idle position during takeoff also seem implausible based on the preliminary report and data from the plane's black boxes. So, what really happened on Flight 171 according to the preliminary report? According to the preliminary report, the aircraft was in perfect condition to fly and in perfect configuration for takeoff. However, the focus of the investigation is on the events during the takeoff roll, which began at 8:07 and 37 seconds. At 8:08:33, the aircraft reaches V1, the highest speed at which the pilot can safely abort takeoff and stop on the runway. However, with no anomalies detected, the takeoff roll continues. About 9 seconds later, at 8:08 and 42, with the aircraft already airborne, the fuel cut-off switches for engine 1 and engine 2 transitioned from the run position or operating to the cut-off position or off, one after the other, with only a 1-second gap between the movement of one and the other. Immediately, the engines began to lose power, since the fuel supply to them had been cut off. On the plane's voice recorder, you can hear one of the pilots asking the other, "Why did you cut off? Why did you cut off?" The other pilot responds, "He didn't do it." At 8 and 52, that is 10 seconds after the cut, the fuel cutoff switch for engine 1 transitions again from the off position or off to the run position or running. 2 seconds later, the air intake door of the auxiliary power unit generator, which is located at the rear of the plane, begins to open. And this is consistent with the auxiliary power unit auto start sequence. We'll understand more about this in a moment. 2 seconds later, at 8:08 and 52, the fuel cutoff switch for engine 2 also moves to the run position. When the fuel control switches are moved from off to the run position while the aircraft is in flight, the full authority dual engine control or full authority dual engine control, which is a computer on each engine, automatically manages a sequence of reignition and recovery by pulling and reintroducing fuel. And in fact, the data shows the exhaust gas temperature of engine 1 increasing, which indicates that the engine is coming back to life. Engine 2 was also able to reignite, but it was not in a satisfactory condition, and the full authority dual engine control repeatedly reintroduced fuel to increase acceleration and recover core speed. A few seconds later, at 8:09:11 UTC, the EAFR, which is the black box, stops recording. Since this is a preliminary report, it does not point out the actual cause that led to the accident. It only presents some data obtained and analyzed up to that point. And, based on this data, it's not possible to know the real reason that caused the fuel supply switches of both engines to transition from on to off position, right at the most critical moment of the flight. The auxiliary power unit. Auxiliary power unit is a generator engine located at the rear of the aircraft, which provides electrical power and compressed air for various onboard systems, usually when the plane is on the ground. It can also be started during flight if needed. The auxiliary power unit uses the same fuel as the plane and generates electrical power for various aircraft systems, such as lighting, navigation systems, and communication systems. The auxiliary power unit also provides compressed air to start the two main engines, and it's used for the air conditioning system and for cabin pressurization while on the ground. When both engines shut down in flight, the auxiliary power unit automatically started to supply electrical power and compressed air to the aircraft systems. However, at no point did the aircraft lose power because it has other redundant sources to supply electrical power. The auxiliary power unit may take more than 30 seconds to start. This is where the ram air turbine or ram air turbine comes in, visible on the aircraft's belly in the videos, which is an impact air turbine used as an alternative source of electrical or hydraulic power in case both engines fail, or failure in the main power systems, or failure in the aircraft's hydraulic systems. The fuel supply switches have a lock that ensures they don't move to another position due to any kind of accidental touch. To move them, the pilot must first pull it back, which releases the lock, and only then can it be moved to another position. These switches normally operate in this condition, so if they need a human action to change position, and there is no kind of automatic mechanism that can make this transition inadvertently, and in addition to that, the panel of these switches on the Air India plane was found with both switches in the correct position, that is, run, indicating that even with the violence of the impact, they remained in the same position, suggesting that the locking mechanism was working correctly. So what could have happened for these switches to change position during takeoff? The report points to another important piece of information. The FAA, which is the agency responsible for regulating and supervising civil aviation in the United States, issued a special airworthiness information bulletin on November 17, 2018 regarding the potential disengagement of the fuel control switch locking feature. This bulletin was issued based on reports from operators of the Boeing 737 aircraft model stating that the fuel control switches were installed with the locking feature disengaged. The airworthiness concern was not considered an unsafe condition that would justify the adoption of an airworthiness directive, which would require the replacement of the component by the FAA. The design of the fuel control switch, including the locking feature, is similar across several Boeing aircraft models, including the 787. After the release of the preliminary report, Air India ordered that the locking mechanisms of all fuel control switches on its Boeing aircraft be inspected as a precautionary measure. However, the inspections were completed and no issues were found. Many theories claim that one of the pilots intentionally turned off the switches in order to cause the accident. However, others point more towards possible failures in the switch component. However, the final conclusion will only come with the final accident report.